Hello, my name is Kyra Miller and I will be presenting on weather forecasting for the state of Texas in the United States. This is my table of contents highlighting everything I'll be speaking on in this presentation. Data description. The data contains an overview of the Global Historical Climatology Network Daily Database. According to the initial application, the database was designed to fulfill the need for daily climate data over global land areas. The data has the potential for many applications, including climate analysis and monitoring studies. This database contains records for over 80,000 stations in 180 countries and territories, producing the official archive for the U.S. daily data. There is a warning stated that while assurance checks are routine, the data is not homogenized to account for the various recording methods throughout the given eras at any particular station. For this project, we will only be utilizing the Texas data contained in the database. Given the size of this database, manipulating this volume of data would require significant processing power that is not readily available, and due to this limitation, our subset dataset will only maintain Texas data. The data attributes that are contained in this data set are ID, latitude, longitude, elevation, year, month, day, precipitation, precipitation value, snow, snow value, snow depth, and snow depth value. Correlation study. The attributes selected for the correlation study were latitude, month, and PRCP value. PRCP value represents the 5-character value of the element PRCP, or precipitation. Based on common knowledge, you can assume that there is a change in precipitation levels as you move away from the equator, tested with the latitude attribute, or as the seasons change, tested with the month attribute. With these 3 attributes, we can expect to see some level of correlation. Results. According to the results seen to the left, there is actually not a high positive correlation between any of the attributes. As seen in the scatterplot matrix, there does seem to be more of a positive linear correlation between the month and the PRCP value attributes than there is represented in the correlation run. There also seems to be a negative linear correlation between the latitude and PRCP value attributes, where there is a weak positive correlation represented in the correlation that was run. There is seemingly no correlation between the attributes of latitude and month, which is to be expected, but there is a very weak downhill or negative linear relationship between the two. While Excel may be a better method when running a correlation between attributes, Excel cannot handle the amount of data being used in this project. QQ plots. For the elements precipitation and snow, we see a QQ plot with a fat right tail, where the data is relatively normal in the distribution until the tail. For the element snow depth, we see a normal QQ plot. The data is normally distributed other than the outlier in the point labeled 4033. Latitude and longitude can be assumed that they are good predictors for our element variables. P-value, t-value, and error analyses. P-value. According to the significance codes, latitude and longitude are excellent indicators of precipitation value and snow value, but only latitude is a good indicator of snow depth value, while longitude is insignificant. T-value. For precipitation value, longitude seems to be the better feature to select, but latitude is the better feature to select for both snow value and snow depth value. We know this because the selected feature is the furthest away from zero, allowing us to reject the null hypothesis. Errors. Assumably, the more features we add, the less error. We can see that this is not the case for the element snow depth, because when we add an insignificant feature such as longitude, the error value does not get less. The features selected were latitude and longitude to predict the elements, because in common knowledge one can assume that where you are has something to do with what kind of weather and how much weather an area would have. This assumption is proven given the information presented. The feature latitude matches one of the features selected in week 2's correlation study. There was not a great correlation between latitude and the element precipitation, but it is seen here in the feature selection that latitude serves as an excellent predictor for the elements, including precipitation. Time series data description. The composition of the precipitation data suggests that there is a 12-month seasonality to the data given the pattern seen in the seasonal plot of the decomposition of additive time series with a frequency equal to 12. There are multiple multi-year periods that we see a trend of heavy rainfall. Example, 1995 to 1998. 2001 to 2003, 2004 to 2008, and 2016 to 2018, versus the long periods of little to no rainfall, example 1998 to 2002 and 2008 to 2016. There are high points of randomness seen on the random plot that coincide with the heightened rainfall seen on the trend plot. It is likely that rainfall can be considered random when it comes to the state of Texas, when comparing participation patterns to other parts of the United States, for example, Washington State, that have high precipitation patterns throughout most of the year represented in the original dataset. Observed data. In the Holt-Winters filtering graph, we see the original data that matches the originally plotted data and the smoother data that will be used in forecasting the future rainfall of the state of Texas. Forecasted data. In order to forecast our time series data and make predictions about future precipitation rates, we utilize the forecast function of R. On the right side of the screen, we can see an example of the data that R computes. Given that we looked at 25 periods of forecasting, we are looking at about the next 2 years, February 2021 to February 2023. In these next 2 years, R does not seem to think that there will be a great spike in rainfall. Due to randomness, as seen on the screen before, we know that this could easily change when time comes. Many of the major spikes we see in the beginning of our forecast for Holt-Winters plot are due to randomness. Locations across the world have an average climate that is typical of an area. We can assume that Texas has a relatively dry climate that experiences intermittent rainfall. This average is upset due to the random events such as torrential downpours and flooding, as well as opposite extremes, a drought, that are common knowledge in the state over given time periods. Autocorrelation. Considering the time series produced from the data in the comparison with itself, we see that at lag 1, with the assumption that 0 is our first autocorrelation, there is an autocorrelation of 1, which is to be expected. When shifted, we see that only a lag of 2 maintains a significance, since it hits at the 95% confidence interval line. Otherwise, if we were to utilize our correlation value between precipitation value and longitude as a threshold, which is our highest correlation between precipitation value and any of the other attributes, we would lay below the significance level required for significant lag. Since the autocorrelation tends towards 0, we have a no or a weak autocorrelation between the time series and itself shifted. Given that the main goal of autocorrelation is to explore the long-term memory of time series, in terms of weather, we see a weak autocorrelation because weather can easily occur at random. We saw previously in our forecasted data that we can make general assumptions about an era's precipitation, but cannot make pinpointed predictions years in advance due to the randomness of weather, as seen in the time series data description, where random events such as floods and droughts will affect a region's average weather when taken into consideration for a period of time. Seasonal ARIMA. Standard residual. The standard residual plot shows the difference between predicted values and the observed data. There are quite a few spikes in the residuals. These spikes match those formerly observed in the time series description trend, where they can be attributed to random weather events. ACF of residuals. The autocorrelation values are inside the border other than 14. There still is not a display that can be linked with seasonality. As seen in the previous slide, this time series has little to no autocorrelation, matching what we saw in the previous slide. QQ plot. The QQ plot shows the high normality with a fat right tail on the right side of the plot. This lends to the data being seasonal in some respect. This is similar to the QQ plots that were done to predict the elements given latitude and longitude values. P-values. The p-values are higher than threshold, 0.01, and the values are higher than 0.05, so we will accept the null hypothesis, which is the residuals are too small. In conclusion, based on the standard residual and ACF of residuals, we do not have any seasonality. We do have a fairly normal distribution, but based on the fat right tail, the distribution is predictable. There is some seasonality due to the fact that the majority of the QQ plot has a normal distribution. Even if we have some outliers in the standard residuals graph, many of them are close to 0. We can predict the future values, but only a few without major error. Moving average and exponential smoothing. Moving average. The smoother data displayed in purple is the product of the SMA function on a reduced sample size. Sampling was necessary due to R not being able to handle the size of the data. The black displays the observed data. Mean absolute percentage error, or MAPE, typically used to measure for forecast accuracy, is equal to infinity percentage, due to a division by zero. This occurs when any real value equals zero, which is true for many of the data's observed values in arid Texas. Exponential smoothing. Using the sample previously used due to a size restriction in R, we would typically want to see that the point forecast is somewhere close to the low and high of the 80% and 90% confident levels in order to assume accurate forecasting. This is not the case, seen in the bottom right. Our point forecast continuously equates to 20.94957 for the majority of the sample. Calculations run into similar issues as SMA, where the MAPE also equals infinity percentage for the same reason previously stated. In conclusion, while I think an educated guess can be made about a day's precipitation rate utilizing the days leading up to that date or weather recordings that fall on the date in the past years, everyone has experienced random weather patterns in their areas. For Texas, it can be assumed that you will have larger precipitation values in the late summer into fall, as well as late spring. In our analysis, we found that month was not a good predictor for precipitation value, where a combination of latitude and longitude was actually an excellent predictor. We were able to find hints of seasonality scattered throughout our data, but it is obvious that something like temperature would be a better example of seasonality. References. In their paper, Long-Term Changes of Heavy Precipitation and Dry Weather in Japan from 1901 to 2004, Fujibe and their co-authors look into statistical trends of precipitation in different Japanese areas over a 104-year period. In their paper, Weather Data Analysis and Design Implications for Different Climatic Zones in China, Lam and his co-authors collect weather data for 5 different Chinese cities that represent the 5 main architectural climates of the world. This is then broke down into common climatic variables to then run statistical measures to be used in the consultation of building services and designs. In Simulation Precipitation by Weather Type Analysis, Hay and her co-authors utilized climatological information in order to perform precipitation simulation. These simulations are assigned to individual days by using observed statistical relations between weather types and precipitation characteristics. These simulations are then used to compare to observed data.